Amsterdam, the Brug. It looks as if it is easily movable, but how was this achieved? A movable bridge was originally used as a passive method of defense. It started with a timber span in a stone bridge. Clever craftsmen, however, invented the prototype of the movable bridge, the drawbridge, which at the cost of much energy could be opened by means of a chain. In the case of a drawbridge, reduction of the energy was achieved by using counterweights. Thus, equilibrium was obtained in the closed position. However, a serious problem was revealed. While opening, an acceleration occurred if a constant force was applied. This was obviously due to the increase in distance between the point of rotation and the chain. So, equilibrium was not achieved in each position. To keep this acceleration under control, the counterweight was sectioned. While moving the bridge, the action of the counterweight is transmitted in parts to the point of suspension on the wall. In a discontinuous way, this was achieved by using metal balls. By rolling a counterweight along a curved track, continuous control was obtained. More viable was the use of balance beams. This led to the bascule bridge with a counterweight in the balance frame. Until about 1800, these bridges were constructed of timber. Afterwards, this material was steadily replaced by wrought iron and later by steel. Now, equilibrium can be maintained in each position, thus requiring a minimum of energy to move the bridge. Integration of the balance frame in the deck gave birth to the bascule bridge. A combination of a fixed and a movable bridge is the transporter bridge, very popular around the year 1900, but now out of date. Remotely related to this type of bridge is the rolling bridge. This entire railway bridge is moved by means of rollers and cables. In this cantilever drawbridge, not only the width of the vessel is important, but also the mast. An old type of movable bridge is the derrick bridge, applied in fortifications and railway bridges. The main girders rotate with respect to vertical axes, placed in a saving in the abutment. This arrangement makes the opened bridge look like it's folded up. A floating bridge is an alternative to make a passage. Here, pontoons fulfill the function of the bridge and support the deck. A system of cables pulls the pontoons under the approach spans to let the ships go through. A next step in the direction of a swing bridge is this pontoon bridge. Another application of a pontoon can be found in a swing bridge with a rim bearing. The pressure on the rollers, due to dead load, is reduced to about 30%. In this way, friction is reduced, and consequently, the energy necessary to move the bridge. At the turn of this century, this system was used in some large swing bridges in England. In a symmetrical swing bridge, equilibrium is established naturally. This symmetry is a necessity in this aqueduct swing bridge. Symmetry because changing water level and the possibility of leaks must also be taken into account. In these two unusual asymmetric swing bridges, two counterweights keep the bridge in equilibrium. One counterweight in the lateral direction, the other in the longitudinal direction. Equilibrium, a basic principle in movable bridges, is most clearly recognizable in a lift bridge. The lift bridge undergoes a vertical displacement. Upwards with a limited air draft. Downwards with a limited waterway depth when the bridge is submerged. Most types of movable bridges did not adequately meet developing requirements and have ceased to be used. 4 types survived. The bascule bridge with overhead counterweight, the bascule bridge, the lift bridge, and the swing bridge. Movable bridges, constructed of steel and applied everywhere. A bascule bridge with overhead counterweight. The structure consists of the movable deck, the tie rods and the balance frame, including the counterweight. The balance frame is supported, in this case, by a portal frame. In this railway bridge, the bracing between the balance beams is missing. Here, the balance frame is composed of two I-beams, including a bracing designed as a Vierendeel girder. A part of the operating mechanism is housed in the columns. It moves the curved rack, thus opening and closing the bridge. In this case, the frame moves in between the columns. The point of rotation is situated immediately adjacent to the column. However, the point of rotation may also be situated above the column. This would limit the angle of opening of the bridge severely. For this reason, an offset column is used. In bridges with an orthotropic deck, separate balance beams are used. The bracing is missing. In bridges with a timber deck, the counterweight is placed in a box girder. In this way, a rigid connection is created between the beams, ensuring that the bridge rises evenly. A one-sided drive becomes possible. The deck of a modern bascule bridge with overhead counterweight is usually designed as an orthotropic deck. It is composed of a deck plate, stiffeners and cross girders. Operation of the bridge is possible by means of a crank connecting rod mechanism. A hydraulic system, or by means of a rack. A steel bar passing through or along the side of the column. The deck may be constructed as a straight or a skew deck. A parallelogram, a basic element of a bascule bridge with overhead counterweight, is recognizable in this complex steel structure. With a fixed counterweight, equilibrium can be maintained in every position. This special type, the Strauss type, was developed in America. Many examples are to be found in the harbor of Antwerp. The choice of a bascule bridge with overhead counterweight is mainly determined by the relatively low price because of the absence of a pit. Aesthetic considerations also play a part. If a wider clearance than about 25 meters is required, a bascule bridge is more advantageous. 60 meters or even more is possible for a single-leaf bascule bridge. Here, the total costs are severely affected by the presence of a pit. A bascule bridge is in fact a bascule bridge with overhead counterweight, in which the balance frame is integrated in the tail of the bridge. The four hinges are replaced by one center of rotation. The section behind the point of rotation, the tail, moves in a pit or in free space. The bridge rotates with respect to a fixed point of rotation which coincides with the center of gravity. For dead load, the bridge should be in equilibrium in every position. Therefore, the center of gravity of the steel structure, the point of rotation, and the point of action of the counterweight must be located in one line. Also, in a Scherzer bascule bridge, the center of rotation coincides with the center of gravity. Counterweight material, usually concrete, is used, often housed in a steel box. By using a hinged counterweight, the lever and the point of action of the counterweight are fixed exactly. The Panama wheel was originally developed by Gustav Eiffel to operate the lock doors of the Panama Canal. It consists of a circular sector with a pull-push rod connected with hinges to the sector and the bridge. An alternative for a Panama wheel is the roller slot system. A rotating crank at the end, provided with a roller, acts in a slot and moves the bridge. The next step in the development is a direct operation of a bridge by means of a hydraulic system. Single-leaf bascule bridges are possible as well as double-leaf bridges. In this way, a greater waterway width can be obtained. An unrestricted air draft can be achieved with a bascule bridge. In a lift bridge, a greater waterway width is possible, but the air draft is limited. The main parts of a lift bridge are the towers, made of concrete or steel, and the deck in between the towers. Counterweights are placed in the towers or outside the towers. The deck is connected to the counterweights by means of counterweight cables. Starting with a design option in which equilibrium between deck and counterweights is obtained at half height, this equilibrium is disturbed when the bridge is moved. The cable length to the left or to the right of the sheave is shortened or lengthened. Shifting the action of the cable weight to the right or to the left. A disturbance in equilibrium induces acceleration. To counteract this effect, a balance chain is installed. Outside the tower or inside the tower. Dead load equilibrium is now maintained in every position of the deck. If the bridge is open to traffic, the deck must be fixed vertically and brought in the correct position in the longitudinal and lateral directions. By means of overweight of the deck or a locking pin, the vertical position can be fixed. A pin necessary for centering in longitudinal and lateral direction also adjusts the rails. Buffers reduce the kinetic energy just before the bridge touches the supports. The locking pin fixes the bridge vertically. For a lift bridge, the width of the deck is of no importance. A lift bridge with only 2 towers was the optimal solution in this situation, with limited air draft and a wide central verge with 2 wide carriageways. In a swing bridge, the width of the bridge should always be smaller than the length in order to achieve sufficient clearance. There is no limit to the air draft. The bridge width determines the diameter of the pier, but pier or bridge width reduce the waterway width. A swing bridge consists of a steel structure with two equal or unequal leaves, supported on one point of rotation. A drive, and the end supports, including a raising device. Counterweight is only necessary in asymmetrical bridges. A plate girder as main girder can be chosen, or a simple cable-stayed girder. A rim bearing changes the swing bridge in service condition into a girder on 4 supports, of which the central span is relatively small. Loading on one leaf introduces an upward deflection of the other leaf, and the reaction on one support on the pier may reduce to 0. To prevent this, the central part is equipped with a light truss system, which allows shear deformation to occur. In this way, the bridge rests on all supports, even if unequal loading is applied. As the roller track of the inner circle is shorter than the track of the outer circle, the rollers are tapered. Due to sensitivity with respect to tolerances, deformations and subsidence may happen, but not all rollers are load carrying. This disadvantage is removed in the modern constructions by replacing the rim bearing by a spherical roller thrust bearing. It consists of an inner and an outer ring in which a carefully machined cage is fitted. In that cage, the spherical rollers can rotate. Based on the principle of pinion and toothed rack, old bridges are simply moved by hand. Remote operation is possible thanks to the developments in electronics. Simply with direct visual control, or from one bridge master cabin, 2 bridges can be attended to. Alternatively, here is a central remote operation where 3 bridge masters attend to 15 bridges. A future development is a system in which, comparable with a train, the vessel opens the bridge automatically. It is of utmost importance to identify a ship for which the bridge must be opened. Therefore, hydrophones, video cameras, and infrared signals are used. The information is compared in a computer. Cooperation, a necessary condition for the application, design, and building of movable steel bridges.